Right. Oh my god. Uh, so we have a CF contest right now. Um, right when I said that, I realized my yogurt was melting, but I don't have time to eat it right now, so it's probably just gonna sit there on my desk and just melt, which is kind of unfortunate, but whatever. I can just freeze it when I'm done with this. It's fine. Okay, but this is Div 2, so it's not rated for me, but I'll still do it because, CF contests are fun. Got a sequence of length n, each operation accepts an arbitrary interval, and for all lists, replace AI. Two to five. You'll want to minimize the maximum value in the sequence. Is it not just the and of all the numbers? Let's try that. I think it's just the and of all the numbers. Oh my god, Codeforces, stop this. Dude, let me submit. Good god. Okay, we got A. Let's go to B. As the story unravels, a timeless tale is told once again. A friend of Mocha's, there are n squares arranged in a row, and each one can be painted either red or blue. Among these squares, some have already been painted, some are blank. You can decide what color to paint on the blank squares. Some pair of adjacent squares may have the same color, which is not perfect. We would define imperfectness as a number of pairs of adjacent squares that have the same color. Okay. Goal is to minimize imperfectness and print out the color of squares after painting. Well, I guess the standard way is to just use DP, but I think another way I think the thing is that we want to mimic a alternating pattern as closely as possible. Or because it's like, if we were to imagine, like, if it was B, this, and B, or if it's like B, BA, or AA, or AB. We could just use DP to solve this, but I don't want to do that because that's just annoying. Is CF crashing? Oh my god. You're kidding me. Okay. I'm just going to open up all these problems. Okay, this seems like graph problem, another graph problem, and GCD. Minimize imperfectness. Okay, so it's like, we set this first character to be we always want to prevent conflict. Like, if we were to have a choice between like R and B, change it to R or change it to B. We also want to change it to R. Yeah. because we want to prevent future conflicts from happening. I wonder if this works. Okay, so for int I equals 0, I is less than n minus 1, I plus plus. That's just the first character. And then after the second character, if I is greater than 0, then if okay, if this is equal to a question mark, then res at I will be equal to whatever is it going to become whatever res at I minus 1 is not, yeah. Otherwise, we want to prioritize making sure it's not the same as this. Array at I plus 1. Yeah. Then res at I equals array at I. Otherwise, res at I n minus 1. Okay, so else it's res at n minus 1 becomes this minus res at n minus 2. Okay, let me just handle the n equals 1 case really quickly. Oh God. Okay. Why am I getting 1s for some of these? Why am I getting... Oh, it's R and B. Oh, oops. I thought it was A and B. Oh. Let's try this again. Okay, I'm just going to submit this to see if it works or not. If it doesn't, then oh well. Alright, look at problem C. City where Mocha lives in is called there are n plus 1 villages and 2n minus 1 roads. Directed roads, okay. n minus 1 roads from I to I plus 1, and then n roads can be described as sequence 1 through n. if this number is 0, the ith of these roads goes from village I to n plus 1. Otherwise, it goes from village n plus 1 to village I. To avoid the trip being boring, they plan to go through every village exactly once. They can start and finish at any village. Can you help them draw up a plan? I want to visit every village exactly once. Where do they start? So they go from 1 to n. Oh, I see what's going on. Okay, well, we got wrong answer. Oh my god. Let's see. I guess we have to debug this. Yeah, this greedy is kind of... It's kind of... Do I just do the DP? I guess I could just do DP. No, screw it, I'll do a DP. Actually, let me solve C first. N roads can be described as a village if that's like this. And the ith of these roads go from village I to n plus 1. Otherwise, it goes from village n plus 1 to I. Okay, so it just determines the direction. So if we have like n cities, and then we have like, we can go along like this. We can, if there's a city that can go out over here and then come back down over here. But we want to visit everything exactly once. So we start at this city. I mean, if there's all these edges are going out of here, then it's impossible. Yeah, so it's like we can go in this direction. We can go up here, we can come back down here. Yeah, okay, C is easy. I'll do C and then I'll do DP for B. Okay, so oh wait, they can start at any village. Okay, I didn't realize that. Oh, right. So like if there's an edge going from here to here. Then we can just go down here, otherwise we can just... Oh, it's always possible then. If we can start anywhere we want, it's always possible. Because if there's some, like, edge that goes from the first node to this n+1th node, then we can just travel this normal path up to here, and then we can like go back. So we take a rightmost one, and then we like go back. And if none exists, then we can just start from this node. Okay, so it's always possible. Okay, it is always possible. Let me just do like how do I implement this? In location equals -1 for an I equals 0, I is less than I equals plus. If so, 0 means it goes from I to n+1. So if array at I is equal to 0, location is equal to I. So if our location is equal to -1, then we know we can go from 4, 1, 2, 3, to like n+1. And then it's like 4 and I is equal to 1, I is less than n, I plus plus. Otherwise, it's always possible to do the path where it's like 4 int I equals 1, I goes up to like less than or equal to location plus 1. But this is like the first step. And then we append this step, and then I is equal to location plus 2. I is okay, let's try this. 1, 2, 3, 4 works for here. 1, 2, 3, 4 works for that as well. Okay, I'm gonna start implementing my DP in the meantime. Yeah. Else we do this. Yeah, that's fine. Public int dex public int. I mean, the parent is always okay. So int parent equals new int at n and then 2. So arrays.fill dp at I infinity. Parent I -1. Okay, and so if array at 0 does not equal to R, then it can be B. Yeah, it can be B. So then it's like dp at 0 at 1 is equal to 0. If it's not equal to B, then it can be R. So dp at 0 is 0 is 0. So if array at I is not equal to R, it can be B. So then it's like dp I, yeah, B is 1. dp at the minimum of I -1 at 0, dp at I -1 at 1 plus 1. So if dp I -1 at 0 is less than dp at I minus 1 at 1 plus 1. Then we know the parent at I and then 1 is going to be 0. Else the parent at I at 1 is going to be 1. So if rate at I does not equal to b, then dp at I 0 is equal to min of the previous color, dp at I minus 1 at 0 plus 1. If dp at I minus 1 at 1 is less than equal to dp at I minus 1 at 0 plus 1, parent at I at 0 is equal to 1. Else parent at I is 0 is going to be 0. Okay. And so while if dp at I minus 1 at 0 is at 1 is strictly less than dp at n minus 1 at 0, then cur becomes a 1. So we're on here. And so if cur is equal to 0, then what did 0 mean again? 0 means it ended with a B. No, 0 means it ended with an R. And cur is equal to parent at I, no, parent at I and then cur. Try this out. Looks like it could be correct. Okay, we got C. I'll look at D while I wait for B to grade, to judge, whatever. Okay, we got B with the DP. Okay, let's look at D1. D2. Okay, difference is that n is 1,000 in here, and it's 10 to the 5 in here. Okay. A forest is an undirected graph without cycles. Okay. Both have a forest with nodes from 1 to n. They would like to add edges to the forest such that after adding edges, both of them are still forests, and they add the same edges. I want to know the maximum number of edges they can add. Huh. Okay. So how do we do this? So oh, we have to output the edges as well. Okay. If we also have to output the edges, how can we do this? And we can think of them as components, right? So if we first figure out the components each thing is in. If we were to add an edge between any two components and they connect components, is that always a good step to make? Match a 3 and a 1. We could have matched a 4 with a 1 to merge the same components, but then that means the 3 is disabled anyway. Yeah, I think that means we can just take things naively. I think. I'm gonna try that. So let's try this. Just adjust my DSC a little bit. So it's N, M1, and M2. Okay. So we have M, and we have the edges, so. Okay, so this we have for I is equal to 0, I is less than. Okay, so we have this many edges. While union 2 dot merge. Okay. So if union 1 dot find A does not equal to union 1 dot find at B, and union 2 dot find at A does not equal to union 2 dot find at B, union 1 dot merge A and B, union 2 dot merge A and B. Let's see if this number matches. That's 0. That's 1. Does this give 5? Okay, it does. Let's try this then. Okay, I think it's the same, like, input, I guess. Okay, we've got D1. Yeah, seems like E is easier than D2, so I'll go to that. Yeah, I think that's, yeah. Okay. N is almost 50. Interesting. You want to be an astrologer. That N stars in the brightness of I stars A at I. You consider this born constellation. It uses these numbers to show its state. A state is called mathematical if all of these conditions are satisfied. Because AI is an integer in a range list. The sum of them don't exceed M, and they're all coprime. Or no, like the GCD of all of them is equal to 1. How many different mathematical states of this constellation exist? Well, immediately we could do something like dp at maybe something like dp at which star you're on, the current sum of brightness, and also what your current overall GCD is. That's a little too big. Yeah, that's too many states. But as m is large, we don't have as many options, maybe. We don't have as many options. It doesn't exceed m. The picture for a second example is wrong. Okay, whatever. I'm gonna go to the bathroom. Alright, I'm back. Got another yogurt bar. And we know GCD will decrease at most log number of times. Mm-hmm. Hmm. Okay, what if for each value, and for each position, we calculate, like for each value, for each position, maybe for each length as well. What would that be? Like 250 times that would be 25 million. Then we could calculate how many assignment of values exist such that the GCD of all these values is equal to this and equal to our current value. Okay, if 1 and 3 are in the same component in here, but we draw 3 and 2. 1 and 2 are in the same component in here. Like, wait, so if it's like 1 and then 3, these are different components. In the other graph, it's the same, they're already connected by an edge. We do 3 and 2, so when this edge doesn't exist, then we can connect them. Yeah, if the edge between 3 and 2 in second graph didn't exist, then we can make an edge over there. Think about E. Think about E a little bit more. AI is... Okay, so it has to be this number in the range. The sum of all of them have to be less than M. We know our current sum, and we know the sum we're about to get. We know the GCD has to be some multiple of the value, or like at most the value we just increased it by. Okay, So we know, for example, if we know like it's our GCD is currently equal to this prime number. Like, well, the GCD of an odd number and 2 is always going to be 1. Okay, so we know like GCD could be like some product of prime numbers, or just keep it as itself. Like, alright, what are some possible DP states we could have? Like DP, this is a stars, which star we're currently on. This is like the total sum. It's possible for GCD to decrease once, and then it becomes a 1. Like, what if we want to calculate this ignoring the GCD condition? Then it's just, it's just knapsack, right? For each transition, and then for each value. These values are possible. If we translate them over here, this new copy of values are also possible. Plus, like, those values added onto some range in here. Yeah. A number of ways to get these values, plus like a number of ways to get those values. And like with prefix sums, we can just compute that in O of n times stars. Or like n times n. Yeah. If it's n times m, then what if we count the... Wait, how many primes are there less than 10 to the 5? It's about 10 to the 4. So... No, that's little. That's little. Not quite right. And we know the maximum smallest number in here is about 10 to the 4, wait, 10 to the 5 over 50. What's that, like 2,000? Yeah. We know the largest the minimum can be is 2,000. Which means the overall GCD to end can be at most 2,000. Or like some very small number. So maybe if we can count it's like currently some number but like if that number is really big, we don't know how it will interact with a number in the future. like each current GCD will have at most, it'll either like carry on to the next thing, or it's just going to get cut in half. So each like GCD state will produce at most log more GCD states. So how would we use like what, a map maybe? Oh, the problem is like we need to calculate these GCD transitions efficiently. Yeah, that seems kind of hard to do. Or is it? Wait, is it hard to do? Maybe not. Maybe if for I guess if we have if we consider GCD maybe not that. What if we did dpn? This is the current sum, and this is the last time the GCD itself has decreased. Or like last index of GCD decreased too. Yeah, so it's like dp. Well, but it can be different values of a GCD, so yeah. What if we ignore the sum condition? Okay, if we ignore the sum condition, then we can just do like dp at n and then the current GCD. Well, it would be hard to transition around here. How would we do that? Like we have some range of values. I guess we want to count the number of ways we want to get a GCD from here to here. Okay, so if it's possible to get a GCD from here, if it's like 2 times that value, then 3 times this value, we can take something out from here. We could do like a C. That just seems annoying to do. Yeah, that just seems kind of annoying to deal with. Let's see. I want to think about D a little bit more. like, okay, so if any two pair of nodes are already in a component in both of these graphs, then we can basically treat them as the same node. Yeah. If they're both, okay, if like two pair of nodes are not in the same component, then I mean, it doesn't really matter. But if two pair of nodes are in one component in one thing and not in a component in another thing, then that's kind of tricky. Because, for example, if this 2 edge didn't exist, then 3 to 1 would be impossible to draw. But we would know that 4 to 1 would be possible. This is a second example. Is it always possible to is it always possible to keep on adding in edges until one of the graphs become a tree? No, it's not. Because at some point, if a component of 1 and then like okay, let's say if 1 was isolated and then everything else was here. If it was like 2 and then everything else was in here, we know we had to connect the 1 and the 2. Oh wait, maybe it does work. I mean, we can prove this inductively. Yeah, so if we have something like this, we know we have to connect this node with anything in here. If they're the same node, then obviously it's just the same connection. If they're different nodes, then we just have to connect this with this, because this node is in this component over here, this node is in this component over here, so that works. Okay. Is that how we do this? I mean, that's if everything was a single node. What happens if we want to merge like these components together? Like if we want to merge two components together, like in here, oh, okay, the sample is fixed, but if we can draw an edge from 4 to 5, okay, so like let's say we want to merge like these. I guess it's like given any pair of two nodes that aren't merged yet, we can just merge them. Like there's always a way to merge their components together at least. Because, okay, let's say like there are roots. Like this is like one like little subtree, this is another subtree, A and B. And like in here, obviously if they're different components in the beginning, we can just merge them and there's no problem. Otherwise, that implies that they're in the same component already, like somewhere, where it's like A and then B. But does this imply that we have some other thing we can merge in here? Like for example, let's say we just had A and then B in here. That means there exists another node, like X, that's isolated, and we can match B with X as long as B and X are not in the same component already. But if B and X are in the same component over here, let's say this is X, then we can match A and X, and then it does the same thing. And because we can match A and then X, because B and X are in the same component, A and X cannot be in the same component. So this will always work if we just draw an edge over like this. Yeah, so if we ever encounter like two components that are like that, there's always a way we can merge it. Like given these two pair of nodes, if we can merge them, then we just merge them. If we can't merge them, but one of them is like in a disjoint like position, then in the second graph in which they are connected, we can just find a third node, and then we can use that node to connect with this other stuff. Yeah, and then even if, like for example, x is neither in neither of these components, we can make a connection anyway, and that still increases our answer by 1 because it's just like its own separate component. Okay. How do we implement this? So if we have I guess we would need like their own subtrees, right? Where we pop where like we store some data structure that like stores these components. We take 2 components at a time from like any one of these graphs, and then we can say if let's see. Okay, so we just take their roots. If we can merge these roots in like both of these graphs without any problems, we do it, and then we put this new component back into our like data structure. Otherwise, we can take this component with x in it, we pop it out of its data structure, and then we do that. Yeah, because if these are disjoint, the only time we can make a new component here is if there's another component existing already, which usually we can do. Okay, I think I know how to do this version of this problem over here. We just need to store, I guess we just need to store int res string builder. Okay, so we have our two like connections, I guess. They're from 1 to n. Yeah, so we could do something like, I guess like a tree set, right? Active is equal to new tree set at integer. Active 1 for int I is equal to 0, I is less than, or I guess we add all of a component, so union 1 dot find at I. Tree set at integer, active at 2 equals new tree set at integer. Active 2 dot add union at 2 dot find at I. Okay. So int res, and so while the min of union 1 dot size and union 2 at size is at least 2, then we can always make an operation. What? Wait, Java, you... Oh, it's active at 1 dot size, my bad. Okay, that's a little better. Then we can do int a is equal to, I guess, okay, if active.1, if it gets added to something, then does it matter? No, it shouldn't matter. Yeah. Active 1 dot first. Active 1 dot remove at a, and b is equal to active at 1 dot first. Active 1 dot remove at b. Okay, so we know that a and b are already in different components. So if union 2 dot find at a equals union 2 dot find at b. So this is like it's like we want to get in x is equal to active 2 dot first, and then active 2 dot remove at x. Otherwise we do otherwise you can just merge them straight up. Except the problem is that we need to know which component it is. Yeah, it's like this is node A and this is node B in some component. We get node A and then node B in some component. We can do like int c is equal to. Well, yeah, we want to active 2 dot remove union 2 dot find at A, and then active 2 dot remove union 2 dot find at B. Yeah, and so we do union 1 dot merge A and B, and then we active 1 dot add union 1 dot find at A, and then we do union 2 dot merge A and B, like these two nodes, and then we do active 2 dot add union at 2 dot add at A. Okay, so that's the easy case, or find. And this is like a node that we can, okay, so we always make one merge in here. And then the merge we make in this case is always A plus B, I think. Or just nodes A and B. Because these are, I think, right? Yeah, that should work. Otherwise we get some component X that's not connected to this A and B. And so we want to check to see if union 1 dot find at A, if it doesn't equal to union 1 dot find at X, that means we can draw an edge from A to X, which means we do well, X is already removed. A and B are not removed yet, so we have to do active 2 dot remove union 2 dot find at A. And then we add our new thing. So we do union 1 dot merge A and then X, active 1 dot add union 1 dot find at A. We do union 2 dot merge A and X, and then we do active at 2 dot add union 2 dot find A. And then we make a, and this is basically a move from A to X. Else, okay, so if A and X are in the same component, we know that B and X have to be in different components. So we can just do the same thing over here with B instead of A. So we do B, 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 and then B and X. And then this like cycle basically, or like in this process just keeps on going. Why are we getting 6? That's kind of weird. Got 0 for this. Got 1 for this. 3 and 2. Can we merge 3 and 2? Yeah, that works. Okay, this over here is kind of weird though. One 7, 2, 6, and then 1, 5. Yeah, because we want to add 7 edges, which is like 2 components. Okay, let me just draw this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There's an edge from, okay, in this first graph we have an edge from 1 to 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then in here we have an edge from 2 to 6 and then 1 to 5. So from 2 to 6 and then from 1 to 5. Okay, so we first merged 2 to 3. 2 to 3 is okay to merge. And then we merged 3 to 4, which is also okay. And then after that we merged 4 to 5, which is also okay. And we merged 6 to 5, which is not okay. Okay, how are we merging 6 to 5? In this case, res is equal to 3. So if res is equal to 3, then ln, how is this happening? It's giving 5 and 6. So it wants to merge these components 5 and 6. Or like, well, yeah. Well, we can't do that. So because union 2 at find at A, so it should go over here, right? Yeah, okay. So what is x equal to then? Okay, well, okay, so this is like the third node that we took out. I took it out as 5. Oh, it can't be its the own component. Yeah, it can't be that component. Okay, okay. I'm actually surprised that this caught that. Interesting. Okay, so if x is equal to union 2 dot find at A, then we need to find a different node. And actual x is equal to active 2 dot first, active 2 dot remove actual x, active 2 dot add at x. This is old x and x becomes actual x. Let's try this. That looks a little better. Hopefully it is a little better. I'm just gonna submit it to see if it works. Oh shoot, wrong answer, pretest 9. Okay, well, do we think that this method works though? We need to make sure that, okay, so if this, okay, so they're in the same component. Okay, so we know that A and B are in different components in the first graph. If they're different components in the second graph, then we can just merge them, no problem. It's like down here. Yeah, we just like remove the components that A and B belong to in here. We merge these nodes in A, and we add like this new component. We merge these in B, and we add a new component in B, and then we do this. Okay. Otherwise, actual x active at 2 dot remove. Okay, active at 2 dot first, and then active 2 dot remove actual x. Yeah, we just need any node that's not equal to the component, this like new component. Like anything that's not in here. Literally just anything. Active 2 dot add x, and then x is equal to actual x. Does that look correct? Yeah, that looks correct. That way, if A and x are in the same component. Oh wait, but these are the edges. Yeah, these represent the components, but that doesn't mean the component. Well, I mean, okay. If they're in different components, then we can always draw an edge between them. Yeah, so if they are in different components, we can always draw an edge between them. Okay, so this is like a node in its own component. If x, okay, so if we know a and x are in different components in the second graph. If in the first graph they're in different components, we can just merge them. Otherwise, we know that b and x are in different components because it's not possible for a and x and b and x to be like in all one component, because then a and b would be in the same component, which would then violate this rule over here. Yeah. Are these values up to n? Yep. So to remove b to x, active 2 dot remove union of 2 b to x. What if I just do like, I don't know, like 500? What would happen? 1 2 2 3 3. Okay, that makes sense. What about like 510? And the only edge is like 3 to 5. Then it'd be like 1 2 to 2 4 to 4 to 5. Okay. Okay, what is it, like 5 2 1? We go from 1 to 2, we go from 4 to 3, and then here we go from 2 to 4. Or, yeah, 2 to 4. Then we can go 2 2 3, and then 3 3 5. Is that correct? 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. So we draw an edge from 2 to 3. Wait, no, the input is 1 to 2, 4 to 3, and then 2 to 4. Okay. So we know we draw an edge from 2 to 3. This is okay. And then from 3 to 5, this is also okay. And this is the maximum number of edges we can add. Yep. As long as we have at least 2 components in each graph, there's always a way we can do it. If these are in the same component, then we take other. Okay, so it's like, if these are in different components, we just merge them. If they're in the same component already, then we take the other component in here, and then we check to see if this is in this component with A in this own graph, and then it has to be, if it is, then it has to be in the B. Okay. Let me make sure I'm not messing anything up. Union 1 at merge, union 2 at merge, A and then B, union 2 at find at B. Active at 1 dot merge. Should I try to stress test this? Okay, if we have 2 DSUs, we just want to, okay, tree set, active 1, active 2. any component in here, but if x was in the component in which a belongs into, then union 2.find.I. Maybe it's this, union 2.find.x. Oh, that would actually make sense. Maybe. Yeah, because if they're just in the same component, then that might be why. Like these are just two nodes. If these are in the same component, then we do this. That would also make sense as to why it broke all the way at pretest 9. Otherwise, if we can't merge these two, yeah. Let's see. Is this the reason why? No, it's not. Okay. Interesting. How many pretests are there? There's 18. Okay, I'm just gonna write a stress tester. X159. De-stress. We've got a DSU over here. We have a thing that solves, or yeah. Okay, so public static array listed integer solve. We have int n, int m, int m2. Okay, wait, hold on. We have n. We have I'm just going to copy these. Just m, union 1, union 2. Union 1, DSU, union at 2. Start from tree set. And then we return res. Where instead we do something like add a at x. Okay, so res.add b at x. Otherwise we add a and b. Or maybe it's a.find and b.find. We'll see. Okay, so this gives us n, m, and then n2. Okay, so nt is equal to okay, so we have this. We have int n is equal to let's just say it's 8 for now. DSU union is equal to new DSU at n plus 1. Int m is equal to some random number. Integer dot nope, math.random times n minus 1 plus 1. Or I guess if we want it from 0 to n minus 1, we can just do times n. Yeah. for int a is equal to int math.random times n plus 1, int b is equal to int math.random times n plus 1. So while union.find a is equal to union.find b, then we change these. Then otherwise we union.merge a and b. And then we do, okay, make a second thing. And then we do same thing over here, except we just merge on the second union find. And 2. So we do this while union 2, test case out of 10 this. Okay. Wow. And DSU, or no, union and then union at 2. Hey, go back. What do you want? Yo, what do you want? Okay, so then we do, how do we do this from here? Hi. Okay, you be good. So, and we didn't actually, no, we do change it, okay. Does this work? No, that doesn't work. New DSU at n plus 1, a rig 1 DSU is equal to union DSU clone original 2 DSU is equal to union 2.DSU clone. Okay, so we just have the initial DSUs over here. Okay, so if original 1 okay, edges dot get I, edges dot get I plus 1. So if original 1 dot find A is equal to original 1 dot find B, then print test case return, otherwise original 1 dot merge A and B, same thing over here with original 2. Okay. I mean, it's only n equals 10. Let's bump it up to 1,000. Nice. Bump this up higher. Maybe like here. if, and then else we always do this. If edges.size over 2, we'll max at m and then m2. M minus 1, no, n minus 1 minus this. Edges dot size over 2. Then we return. Oh, okay. Interesting. So it might be like just not the correct size. Okay, 8, 1, 1, 8, 5, and 4, 3. We have 5 edges. Oh, it's only adding 6 edges. Oh shit, okay. That should not be happening at all. I don't know why. Let's try this. Yeah, this should definitely not be happening. I'm only adding 1 edge. I should be able to always add 2. Hold on. So, actually maybe not. No, actually yeah, it depends on how many components there are. Maybe not. Let's see. 1, 2, 3, 4, 5. We merge 1, 3, and 1, 5. This is the first graph. In the second graph, we do 1, 2, 3, 4, 5. Oh yeah. 2, 4, 3, 5. Yeah, it's slightly different. But all of these have 3 components, so it should be working for this test case. So we found something that broke either way. 5 and then 3. It says the only edge I can add is 2 and then 1, which I feel like is definitely not true. Because if we have like 2 and then 1 over here, what this means is that it means that this is happening. 2, 4, 1, 2, 1. So in the first graph, we look at nodes 2 and 4, which is okay. So nodes 2 and 4, they're in the same component over here. So that means that we go over here. Okay, so we should get what our x is in here. Like what node component is in here? It's 1. Yeah, because this is 1 over here. We want to merge 2 and 4 together. We want to merge one of these. Okay, so 1 and 2 end up getting merged together, which is okay. If union1.find, then active2.rem. Oh! Oh, shoot! Oh, okay, I know why. Oh, wait, how did I not pick this up? Wait, okay, I'm just stupid for not picking this up, for not realizing this. Okay, I know why this is wrong now. Okay, so we know we can merge a and x, but it's possible that x is its own component. So if x is in its own component, then we have to like handle this a little bit differently. Because we have to like remove 2 things, not 1 thing. Yeah. So I guess one way to reword this is if union.find at b is equal to union.find at x. Else if union1.find at a is equal to union at 1.find at x. And then else means it's not equal to either, which means we can pretty much merge it with anything, but we have to like do these operations a little more differently. Because we do active at 2 removed union at find, union 1 at merge, a and then x. Yeah, because the thing is that we need to remove nodes. Like we need to remove the x in this original component. So it's like, the way we have to handle this is if we do this. How do I say this? So if union at find at a is not equal to union at find at b, then union at 1.merge, active 1.add, union 2.merge. Yeah, pretty much what happens is we take x, we want to make sure that, okay, make sure it's the same thing. We union, okay, if they're not in the same component, then we need to remove a few things. So for example, because 1 is in this component, we need to do active 1.remove union 1.find at x. Because the only thing we removed, because we removed the original a and b over here, but we need to also remove the x. And then we need to add back the a and the b. So if we found, or like if we, for example, if we were to find that, should I just rewrite this? I think we're just going to rewrite this. Okay, if we're not, so we connect a and x. Otherwise we connect b and x. So the way it works is if a and x are not in the same component, we need to first remove. Okay, well but if b and x are connected in here, then so if active 1 dot contains union 1 dot find at x, active 1 dot remove union 1 dot find at x. Okay, so this removes x, union 1 dot merge a and x, and then active 1 dot add union 1 dot find at a. And then this is like the first step. And then the next step is we can do, we also have to handle what we do in here. So in here x is already added, but union 2 dot remove union 2 dot find at a, or active at 2. Yeah, active at 2 dot remove, and then do union 2 dot merge a and x, and then we do active 2 dot add union 2 dot find at a. Okay, that makes a lot more sense. And then it's basically the same thing over here, except we replace all a's with b's. B's, B, B, B. Yeah. And then in here, like that part is the same. Okay, so let's make sure that this prints 2. Why do I have some, oh, if active at 1 that contains union that find this, then we can remove it over here. It's still giving 1 and 2, 1. Why? Why? Ugh, akabaga. So we connect 1 and 2, we connect 1 and 2. We can still connect 3 and 4. Like, that's still a valid option. System.out.println union 1.size. No, active at 1. Ugh, like, I know how to do this. It's just, I didn't implement it very well. Like, I think, I'll be happy if I can get this. Okay, active at 1.size. Okay, so I got basically 1 and 2. Active at 2.size. This should be relatively big. 3 and 3, yeah. It should have been at most 2 and 2. So why is it 1 and then 2? Oh, because I forgot to add back a component I didn't use. Yeah. Connect A and X. Add component B back. That's if union1.find at X does not equal to union1.find at B. Then active at 1.add union1.find at B. Add component A back. If union1.find at X does not equal to union1.find at A, active 1.add union1.find at A. Okay. Let's see. Wrong problem. Five. One. Running on test 1, test 1, test 1, test 1, test 6. We got E2. Nice. Nice. We need to get E. Okay, that was just, I just had a pretty stupid bug, but, you know, it's okay. It's okay. Okay, what do we do next? I guess E. Yeah, we have to do E. I'm honestly not sure how to do E, which is kind of funny, because apparently it's a lot easier than D2. But whatever. Denote the GCD. Maybe you could just do like DP based on how many decreases occur. Like N and then M. Okay. So N, M, and then left equals new intent. Like something like this. I don't know. Like left at I, and then right at I. I'm gonna Hold on. Okay. We have to. We have about half an hour to get this problem. Um. I wonder if there's any hacks going on. Not like it really matters to me, but I'm just curious. There's a lot on A. What was problem A? It was and of everything? Really? I mean, it doesn't overflow. Whatever. Yo, am I just breaking on E? It seems hard. Like, definitely harder than G. Oh, maybe I'm just breaking. We do DP. Maybe it's like for, we have like just a range, and then we do DP depending on how much we increase it by. We have the sum and then this corresponding GCD with it. Yeah, but like based on these previous numbers, you always want to do it in order of the, like given this number and then this number. Maybe for each number it's better. It's easier, maybe it's easier to calculate that. Like how many numbers, how many ways exist such that its GCD is at least 1? Like if it's at least some big prime, if it's like some prime number, the GCD is a multiple of some prime number. And then we might be able to use PIE to figure out how many times it exactly works. Maybe. Like for each way, we choose like a multiple of that. Yeah, so then we get like, this is a number of ways we can choose values such that the GCD is equal to some number. Or like, for example, the GCD is equal to, or like some multiple of that. Okay, that actually might be how we do it. So DP at G, number of ways to choose n stars such that sum equals m and GCD is divisible by m, or by G. Yeah, then it's actually pretty easy because then we just have like this many ways and then we can just count it like this, and then we potentially just use PIE to calculate the exact number of ways, and then we just subtract it out of the total number of ways such that I remember doing a similar problem to that, to the problem I just said. It was, how long ago was it? Yeah, I think it was this one. No, it wasn't. It wasn't that one. Wait, which one was it? Oh, I think it was this one. Yep, it was this one. Okay, let's try that. I might be able to implement this in 24 minutes. Maybe. I might be able to. Because it's just a sieve, right? We have new long up to 100,000. V is less than or equal to 100,000, V plus, and it's like some sieve logic over here. long dp is equal to new. Long dp is equal to new long, like, we need m memory though. Or I guess if we divide it by that, we don't actually need it. Okay, so int capacity is equal to, the capacity is equal to m plus 1 less than or equal to m. This is like, the way we can do it such that GCD is equal to m. Yeah, the capacity is equal to m over, like if each number has a GCD of like that much, then we can just do it. Then we just divide everything by v, and then just say this is our current like capacity. Yeah, because if it's like 5/3, and we want GCD be 3, we can only have at most one number anyway. So long dp is equal to new long at capacity plus 1. Okay, so for int I is equal to 1, I is less than or equal to I is less than or equal to right. Okay, so for int, okay, so for each value we have, okay, so we have a number of ways to do capacity 0. There's exactly one way. Capacity plus 1. And then we do for int v, for int I is equal to 1, I is less than or equal to right at t. And we increase its value by v, because we know it has to be divisible by this. Yeah. So if I is at least as big as left at t, then we can use this value. Int d is equal to I over v. And then we just say, like, for example, for each value in capacity, oh yeah, and then it's just like ArrayList.add. ls.add I over v. Because like, we can use this number, and then we can say for int d and ls, we can do for int I is equal to start at capacity greater than or equal to 0, I minus minus. So if I plus d is less than or equal to capacity, then dp at I plus d, add on dp at I. If dp at I plus d is greater than or equal to mod, then we decrease it by mod. Okay, these are our updated dp values, I think. Or no, like this is like how many different ways we can do it. And then we do dp is equal to next. And then we do for long x and dp, ways at v, add on to x, ways at v is, and we decrease it by mod. Okay? So now this is equal to the number of ways that exist such that the GCD, yeah, so it's the number of ways that exist such that the GCD is divisible by this. But we want to care about how many ways exist such that GCD is equal to that. I'll just copy the snippet over here. D is at most m. Yeah. D plus D. D is less than or equal to n. V increases by D. And then we do like dp, ways at D, subtract out ways at V. If ways at D is less than 0, ways at D mod ways at 1. Let's see. Line 46, we do capacity plus 1, my bad. 4, 251, and some large number. Pretest 1, pretest 3, pretest 4. Oh, it's going to TLE, isn't it? Okay, how are we going to fix this? Maybe we could probably improve this step over here. Because there's n times m. This part over here is like a sieve. Yeah, I got TLE. Next, at I plus D plus equal to D at I. Yeah, it's like we have some number of ways. Yeah, we have like 1, 2, 3. We can increase these values by 1 or 2 or 3. All we care about is the sum of a dp. Capacity is m over v. This area is at most this much. So we know that the memory itself isn't getting too big. Yeah, like memory itself is fine. Maybe it's just a time limit, probably. Like it's definitely a time limit. V is equal to this number. Oh, let's not add. Okay, so it's I over V. We can do something like this, probably. Oh wait, hold on. Then we do II is equal to II if II plus D. Yeah. Let's just say like 5, 100,000, 1 to 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 100,000. Why is that so slow? Okay, so maybe that's not the best way to speed it up. Alright, we just need to count how many ways. Oh, I guess it's like 100,000. Like when V is equal to 1, It takes 100,000. Wait, but then does the capacity over m, so it's just 1. The capacity itself is just 1. Oh, but if it's like maybe square root at I, then it's like an I, then this loop itself is over I, yeah. Using an account. Okay, so basically given we have like some buckets, in each bucket we can choose like some number in each bucket. If we need to choose at least one number in each bucket, how many ways can we choose numbers such that the total capacity doesn't exceed some number? Yeah, so it's like in here, this is a number of ways we can, maybe like over here instead, we capacity minus d, will that help? No, it doesn't. This part I probably don't need to speed up. Okay, so this is like, this bucket is equal to this many. Valid at 0 is equal to true. Array list at integer, else equals new array list at integer. ls.add at 0, because 0 is the only like valid transition. Yeah, and so then we do something that's like for each, for int x in, for int I, for int a in this array list, we do next, okay, well if, because a is increasing, so if a plus d is strictly greater than cap, then we can break. Otherwise we can do next at a plus d, add on dp at a. If next at a plus d exceeds mod, then we can take care of it. Okay, so if we took care of mod over here, then dp becomes next, and then ls.clear, oh look at, like ls equals new array list at an integer over here, for int I is equal to 0, I is less than capacity, I plus plus. If dp at I is greater than 0, ls.add at I. Does this help at all? Maybe, because it's like knapsack, right? Nope. Oh, how do I speed this up? Aga baga. This number is still right. I feel like I'm just being kind of stupid right now. Like there's definitely a different way to do this that isn't just completely dumb. Like maybe there's a combo way? Oh wait, okay, I'm just stupid. Oh wait, okay, I'm actually just stupid. Hold on. I just realized something. Gee, oh my god, I'm actually so dumb. Okay. I think I've realized a way how to do this. So it's just array list to integer. Like 0 to 3. Yeah, oh my god. Static final int max is equal to inverse factorial 0 is equal to 1L. Wow, I'm actually so stupid. Okay, so we need static long factorial and inverse factorial. So 4 int I is equal to 1, I is equal to max, I plus. Factorial of I is equal to factorial I minus 1 times I mod. Inverse factorial at max is equal to power factorial at max minus 2 mod. Inverse factorial of I is equal to inverse factorial at I plus 1 times I plus 1 mod. Okay, so you've computed you computed inverse factorials. So you have capacity, we have long dp. We have array list at, no, we have int mins is equal to 0, int total is equal to 0. Maybe like 2 million? Sure. I don't even care. Like 1 million. Okay, so mins and then total. If I is greater than or equal to left, then we have D. Int min is equal to int m1 is equal to D, m1 is equal to min of itself in D, max equals max of itself in D. So we do this part over here, and then we can say mins, we add m1 to mins, because that's like a minimum number that we can increase it by, and then total, which is like the amount of extra total we can have is equal to, the amount of extra total we can have. It's equal to max minus m1. Okay, so if mins is less than or equal to capacity, then it's just 4 and extra is equal to 0. Extra plus mins is less than or equal to capacity. Extra plus plus. Long ways is equal to NCR total and extra. So if our extra is strictly greater than total, then we break. Otherwise we do long coefficient is equal to factorial at extra times, factorial at total times inverse factorial at extra. Then coefficient is equal to coefficient times inverse factorial at total minus extra mod. And then we do ways at V, add on to coefficient. If ways of v is greater than or equal to mod. Ways of v minus equal to mod. Oh god. Oh god. Mins. Like 4 over here. That's 6. Why is it equal to 6? M1 is equal to min of itself, M1 is equal to max itself in D. Oh. If M1 is equal to inner.max value, then we continue. Because that means we don't have a choice in here. Oh wait, we continue outer. Because that means like there's no way whatsoever we can do it. Oh, by outer, it should be yeah. Because then that means there's like, if there's no way to do it in here, then there's no way to do it in here. Total times inverse factorial extra, total minus extra. So among like the total like things that we have, if you want to take 0 extra, then there's obviously this many ways to do it. Otherwise we have a total number of ways to do it. Yeah. And then we have this many number of ways to do it and so on. Power factorial max minus 1 I greater than or equal to 0. Okay, times this. Yeah, that looks correct. And then mod. Ways. Wait, it's like this coefficient. This is how many ways we can get this number over here. Yeah. Println mins plus total plus v. Mins total. Yeah, we need to get a minimum of 2. The amount of extra total we can have is 3, but the capacity itself is at most like, and here's at most 4, and here's at most 2. We can get a 1 and a 2, so we can get at most 2 things, but we have 0 extras, and the capacity itself is at most 2. So ways is now equal to oh my god, I don't know what's wrong with this. I don't know what's wrong with this. X1 F92. Oh my god, I think I have the right idea for E. I want to like implement it. Okay, I'm gonna like debug a little bit, like using my like TLE code. Like oh my god, I'm so close to getting it. Like I know I'm close to getting it. 1721. Okay, so this code printed 1721. If I run this, it'd be 1021. Wait, why is it 10? Wait, why is it 1 and 0? line 58 maybe? Oh, V, oh, ways at V, my bad. So it should be 1521. It's supposed to be 5. Why is that? Maybe my, oh wait, this formula is wrong, isn't it? This is like saying, yeah, this is saying like these balls are indistinguishable. Yeah, that formula is kind of wrong, but the idea I think is generally correct. Okay, whatever, that's my contest. I want to debug E, and then after I debug it, I think I'll be able to talk about solutions to all the problems. So yeah, see you then.